you through some of this ecological pyramids POGIL. All right, so we are going to continue working on this on Tuesday, and it will be due on Wednesday at midnight. All right, everybody, so let's go ahead and take a look. So from our previous time in class, we took a look at some of the first page, but I'm just going to kind of review that for those of us virtual folks who perhaps haven't gotten started on it yet. So let's go ahead and begin. So every organism in an ecosystem is either eating or being eaten. When cows eat grass, they obtain some of the energy that the grass transferred from the sunlight it absorbed. If cows could carry out photosynthesis, would they have access to more energy than they get as herbivores? Which organisms in an ecosystem require the most energy to sustain life? So this is our ecological pyramids activity, and our guiding question is, how does energy flow through an ecosystem? So here we have a pyramid of energy. So we see that the amount of calories available at each level is going to differ, and it's going to be less. However, we're going to see it's not exactly 10%. So if we were to take 10% of this value, it would be a little bit different than what we see. So that rule of tens is not a hard and fast kind of universal rule, but we're going to have to calculate essentially what percentage of our energy goes from one trophic level to another. So here it will tell you what type of feeders you have, that your oak tree leaves are your producers, your primary consumers would be your caterpillars, blue jays, secondary consumers, hawk, your tertiary consumer or carnivore. So let's go ahead and begin. It also tells us how much sunlight hits the Earth's surface. So that is over 3 million kilocalories, which is a massive amount of energy. All right, so a unit used to measure energy is the kilocalorie. What is the source of all energy in the pyramid in Model 1? So as we see here, the answer is going to be the sun. So that is the source of all energy. That is our source of all energy provided to a food web and provided to our ecological pyramid. So that is why they put the sun at the base of this pyramid. However, it's in a dotted line because officially we put the producers at the base of our pyramid. All right, so the sun's energy, or the sun, we would say. Number 2, how much energy does this source provide to a square meter of the Earth per year? So we need to think about essentially a quantity, a number. How much does it provide to the Earth per square meter per year? So that is going to be this value, this large 3 million value here. So let's see if I can move that a little bit. So it's going to be 3,190,000 kilocalories. That's how you would write that out. kcal for short. That's the abbreviation. What are the 3 consumers according to Model 1, and what is the producer? All right, so first let's start with the producer. It tells us right here on the side of our pyramid what will be what. So the oak tree leaves are the producer. So the producer, oak tree leaves. Consumers are going to be the ones above it. Whatever is eating the primary producer is the primary consumer. So the caterpillars are a consumer. Also, the blue jays, the bird that eats the caterpillar, would be a consumer. Blue jays, and also whatever is eating the blue jays, the hawk. The larger predatory bird is the tertiary or third level consumer at our 4th trophic level. Remember, 1, 2, 3, 4. It's a little bit different than how we name consumers. All right. So number 3, the arrows in Model 1 represent the energy available to the next level of the pyramid. What percentage of the source energy or the sun's energy from question 1A is absorbed by the oak leaves in Model 1? So now we need to think about it in terms of a percentage. And how we figure out a percentage is by taking our small number divided by our large number, and then we multiply that value by 100, and that will give us whatever X% is. So essentially that is the formula that we are going to use. In this case, we want to know what percent of the entire sun's energy, so that's going to be our large value, this 3 million, do the oak leaves absorb? So the oak leaves, we find, only get 25,500 kilocalories out of that 3 million. So we can go ahead and we can take 25,500 divided by 3,190,000, and I will type that into my calculator. And if you don't have a calculator, you can go ahead and type that in on Google, and it will give you a value for it through Google Calculator. So it'll give you that value, and then we're going to multiply that value by 100. It will give us this value, 0.799%. All right, so times 100 equals 0.799%. Now that is a small fraction. That is less than 1%. So less than 1% of all of the sun's energy can be absorbed by the oak tree. So not overly efficient. However, the sun produces a lot of energy. So even getting a small fraction of it is quite a lot of energy. Okay, by what process do the oak leaves harness this energy? So think about what we have talked about in the past and what you would learn greatly about if you take botany. So the process of photosynthesis is what that is going to be. So recall photosynthesis. Plants utilize light. They take in light, they take in water and CO2, and they produce oxygen and sugars. So that process is going to be called photosynthesis. You've probably heard of that process before. In Latin, we could break that down to photo, meaning light, synthesis, meaning creation of energy through light. Number 4, describe how the consumers in one level of the pyramid obtain energy from the organisms at the previous level of the pyramid. So let's think about this for a second. How would the caterpillar get energy from the oak leaves? What would it do? Would it just stare at the leaves and be like, give me your energy? Oh, wise leaves? No, it would not. It would have to go and munch on those leaves, chew the leaves and eat them. So by eating them is how it would get the leaves energy. And the blue jay would have to swoop down and grab the caterpillar and swallow it whole and eat it in order to get the energy from the caterpillar. So it's by consumption, by eating. So the higher trophic levels must eat the lower ones. Or you could say consumers consume or eat the organisms below them on the pyramid. That's probably a little bit wordier than you need to get, but that is kind of what we're looking for there. Refer to Model 1. How much energy per year do the caterpillars in Model 1 obtain from eating the leaves in a square meter of the oak tree? So how much energy do the caterpillars get from the leaves is the question here. All right, so we need to go ahead and think about that one. How much energy per year do the caterpillars get from the leaves? So now we're not looking at how much energy do the leaves have, which is this 25,000. We're going to be looking at how much the caterpillars have. So which of these values is going to be the caterpillar's energy? It's going to be the 4,000. Let me just double check that I am indeed on the right track here. And yep, that is exactly what we're looking for. It is the 4,000 kilocalories. All right. Now, so that's a quantity. That's just the sheer value. But now we want to know what percentage of the energy originally available by the oak leaves is passed on to those caterpillars. Okay. So we need to think about how much do the caterpillars have? How much energy do the caterpillars have? It's 4,000 kilocalories. How much energy did the oak leaves have? That's the 25,500 kilocalories. Now we're going to use that same formula. let's go ahead and get that same formula. Small number over large number times 100. That will give us 4,000 divided by 25,500 times 100. And I wish I could make that look a little bit better mathematically, but we can plug that in now. We can plug that in. All right, so that, and then we multiply by 100. Looks like it's right about 15.68%. I'm going to go out to as many decimal places as I can just for precision. Was it again 15.68%? All right, so it gets a little bit more than 10%. You see how that rule of tens is not always universal. All right, so what percentage of the energy absorbed by the oak leaves is not passed on to the caterpillars? Think about this as like a pie chart. So if we have a pie chart, so if we've got a pie chart, say we, think about this as like a whole pizza pie. I'll make it a little bit smaller. So if 15.68% of that pie chart is being passed on, we need to think about how much of it is not. So a pie chart represents 100% of a quantity. So it'll be 100% minus, and the percent icon. All right, so it's going to be 100 minus that 15.68, which is going to give us a value of 84.32%. And I'm being very, very precise here. You don't have to be exactly that precise to that many decimals. 84% of the energy is not passed on to the caterpillar from the oak leaves. Now, we have to think about some possible uses and or products of the energy that didn't contribute to the production of biomass. So I'm going to give you one example, and I want you to think about some other ones. So, and with your group, we're not actually going to do this as a group, but a lot of this energy might have been lost as heat. Lost as heat. Used in cellular respiration, perhaps. And you can think about other ways, other places and processes where that energy could have been lost. So brainstorm another one of those. So fill in that blank. Make sure you give 3 reasons. All right, so number 6, calculate the percentage of energy that is transferred from one level of the pyramid in Model 1 to another for all of the levels. All right, so if we can think about that, oak leaves to caterpillars, we already know. Oak leaves to caterpillars was this value. So we already know that, and let me just double check that that all makes sense. Yep, it's going to be approximately 16%, so you can round up if you would like. Caterpillars to blue jays, so go ahead, and I'm going to let you do this one. So think about essentially a small number, the same formula. That is the formula that you're going to be using. Small number over the large number, and then times 100. And I'll give you a hint. So essentially the blue jays energy is going to be smaller. The blue jays energy over the caterpillars energy times 100 equal something. So calculate that one, and we'll do this one together. Blue jays to hawk. So blue jays to hawk, the hawk is higher up on the energy pyramid. It's at the very top, at the capstone of that pyramid. So that's got 24 kilocalories, and the blue jays have 470, and that should help you to answer that other one in 6B. So 24, I think it was. 24 over 470. So we got 24 kilocalories for the hawk, just the small number, less energy the further up you go, and then 470 kilocalories as the caterpillar, right? Times 100. So let's figure out what that is. You can go ahead and type that in your calculator. For 470 times 100 is going to give us about 5.1%. 5.1% would be how much is passed on from the Blue Jays to the Hawks, so not very much. Now 7 is calculate the average percentage of energy that's transferred from one level to another using your answers from question 6. All right, so in order to calculate an average, what you got to do is you got to add up all of the numbers. So you'd go like number 1 plus number 2 plus number 3. So essentially I'll say energy percentage number 1 plus energy percentage number 2 plus energy percentage number 3. And then you're going to go ahead and you're going to divide all these. So if we think about these mathematically, we take the sum of all these, we divide it by how many numbers we have, which is 3, and that will give us the answer. So if we set this up, we're going to have our 15.68 plus our whatever that value is for the second energy. You've got to calculate that, plus 5.1, all that divided by 3. So calculate that out, and I'm seeing that we should be getting somewhere in the range of an 11%. So we should be somewhere in the range of 11%, so make sure you get that, or somewhere thereabouts. So, and then individually write a statement that describes the pattern of energy transfer among consumers within a pyramid of energy. So this is like your conclusion. What did you see? So that's what we're looking for there. What did you see? How much energy got transferred on average? Why might that be? Maybe what did you see and why? Okay. 9. What percentage of the caterpillar's original energy is available to the hawk? All right. So we can talk about this. We can talk about what percentage of the oak leaves original energy is available to the hawk. All right. So if we're looking caterpillars to hawk, we would be calculating a little bit differently. So caterpillars have 4,000. Hawk only has 24. So we'd have to do, the small number, which is the 24 kilocalories, over the 4,000 kilocalories, and that would give us a very small percent. So I'll give you an example for this here, and then you're going to follow that process down there for that one. 24 divided by 4,000 times 100, which is 0.6% of the energy of the caterpillar's energy. So not much of the caterpillar's energy is available to the hawk. And then use that same process right here. To answer that one, number 11, explain why an energy pyramid in any ecosystem typically is limited to 4 or 5 levels only. So think about how much energy is left at the top. A lot or a little? Think about that 0.6%. Is that a lot or a little? And use that to kind of explain why in number 11. Number 12, propose an explanation for why populations of top carnivores such as hawks are always smaller than the population of herbivores such as caterpillars. So if we look at a pyramid of numbers, it is going to highlight that exact phenomena, that exact observation. So think about, I'm going to copy this, think about why there's only one osprey while there's many, many, many more shrimp in this example. So essentially, how you complete number 12 is just explain why you think the phenomena exists of what you see in this ecological pyramid. So why are there so few osprey with so many freshwater shrimp? And it has to do with how much energy is available to them. So explain that, number 12. Number 13, we then move on to our next section. So each level in the pyramid in Model 1 is a trophic level. The word trophic refers to feeding or nutrition. Model 1 shows one example of one organism that would be included in each level. But each level in an ecosystem includes many species of organisms. Number 13, list at least 3 other species that might be found in the trophic level with the oak trees. All right, so if we think about the trophic level with the oak trees, they are producers. So what else could be a producer? What else could be on that first trophic level? So maybe I'll say grasses. And then name 2 other potential producers. All right, 14, list at least 3 other species that might be found in the trophic level with the blue jays. So the blue jays are going to be in our omnivores, okay? Our omnivores. They eat the caterpillars. So we could think of them as what else would be a secondary consumer? What else might eat the caterpillars? So perhaps some other bird species might eat the caterpillars. So I could say robin might eat the caterpillar or a worm, and then name 2 other potential secondary consumers. So think about other birds perhaps, or other things that might eat a caterpillar. All right, and in Model 2, a pyramid of numbers. This is really what this pyramid up here was getting at, a pyramid of numbers. So, all right, let's take a look at these 2 pyramids. Pyramid A, 2 oak trees, whereas Pyramid B has a whole lot of smaller producers, which are leaves. Number 15, compare and contrast the 2 pyramids in Model 2. List at least 2 similarities and 2 differences. So we'll have some. So I want you to list some similarities, list some differences. Think about those. I'll give you 1 similarity. So we can think about there are very few hawks or top consumers in both. And for the differences, I'll give you a clue. So look at the producers. What's different about them? Think about that. So list 2 of each, 2 similarities, 2 differences. Number 16, how does the number of organisms change as you move up the levels in Pyramid A compared to Pyramid B? All right. So in Pyramid A, we see that essentially as you move up the levels in Pyramid A, you have pretty much an identical number of organisms in terms of your primary consumers, your secondary, and your tertiary. The big difference lies within the producers. So I might say something to the effect that above the producers, the pyramid of numbers is identical. Above the producers level, or first trophic level, the pyramid of numbers is identical. 17, are the producers levels in the 2 pyramids in Model 2 referring to the same organisms or different organisms? That's a good question. Now we get into kind of the question of semantics and like naming. Like, okay, so if we got 2 oak trees, each oak tree maybe has 50,000 leaves. So are the leaves separate living organisms or a part of the oak tree? So I want you to argue your case. What do you think there? Are all of these oak leaves a part of one big organism, an oak tree, or is each leaf a separate organism? So are they the same or are they different? I want you to take a stance there and explain why. Which of the 2 pyramids in Model 2 gives a more accurate amount of what occurs in this ecosystem? All right, so which of the 2 pyramids essentially provides a more accurate depiction, perhaps? So we can think about the oak trees as full units of energy. but just having two of them might be kind of misleading. And just essentially what they are, trees are kind of a collection of photosynthetic units called leaves. So I would argue that B is probably a better estimate and a better representation of what occurs. So B, perhaps, because it represents all of the photosynthetic units within the larger organisms. And just talking about one large oak tree doesn't really highlight, say, like how much energy does it produce. Talking about the leaves is a little more accurate to how much energy it produces, because leaves are producing the energy, not the roots, for example. So you need to think about what's actually doing photosynthesis and producing the energy. On our last page, so I'm going to leave you to do some of this. So model 3, pyramids of biomass. Now we can think of the energy pyramid in terms of, or the ecological pyramid in terms of how much living material we have. Okay, so biomass is measured as grams of dry mass within an area. What is the mass of the oak trees in Pyramid X of Model 3? So what is the mass of the oak trees? So go ahead, think about that. It can be found on this diagram. So what is the mass of oak trees? So it should have a value in grams. All right, now in 20, what is the mass of the phytoplankton? So this also should have a mass in grams. So let's think about that. Mass in grams of phytoplankton. You just double check, make sure I'm following along with everything good. I believe I am. All right, yep. It's just going to be essentially those gram values, so nothing too difficult there. And then refer to Model 3. Identify the trend in biomass as you move up the trophic levels in X for this one, and then the trend in Y. So the trend in X, what's happening as we go up? Notice these boxes are getting smaller, less and less biomass as we go up. Why is that? Less biomass as we go up. As we go up the trophic level. So why do we think that is? So one explanation could be perhaps that essentially there's less energy as we move up. So less energy can support less living material and less organisms, less numbers of organisms, like in a pyramid of numbers. We could think about that. So based on that information, is the trend in biomass in Pyramid X the same as Y? Argue yes or no, and explain your answer. So is the trend going to be the same? Pyramids look a little bit different, so see if you can explain why. All right, everybody, so that was kind of your guided walkthrough of the ecological pyramid POGIL. This is going to be due on Wednesday night at midnight, so make sure that you finish that up before class on Thursday when we meet via Google Meet. Also, make sure that Edpuzzle video is all done, so you're getting credit for watching that Edpuzzle video on ecological pyramids. All right, everybody, thanks for tuning in and have a wonderful day.